All right, so in this video, I'm going to be going over an introduction to exponential functions. Basically, I'm going to, explain what they are, how they work, what makes them, unique and special, and how to evaluate them and graph them. So let's get going. So we got the definition here. So we got a function that relates to variables x and y, x being independent and y being dependent. And we have that the key thing is that x is changing, let's say by one, a constant difference, 1, 2, 3, 4, but y is changing by a constant factor, meaning multiply. But it's a little more than that because what we get is a equation that has the variable x as the exponent. We have y equals a times b to the x power. So the key thing is to recognize that the variable x is the exponent or power. I also like writing it so that the b is in parentheses because it helps really emphasize that the b is being raised to the x power. And a couple things that are important. We need to make sure that a is never 0 because that wouldn't make sense. If it is, it would just be 0. And a is also going to be the initial value of the function, which I'll explain when we do the first problem. And b is the base, and the base b cannot be equal to 1. Because if it was 1, it would just be like 1 times 1 times 1 times 1. So it would not change, and so it wouldn't be exponential, which would be pointless. And we're also going to make it so that b has to be positive. So b has to be greater than 0. So let's first look at some patterns to get our intuition going of how an exponential function is different from the linear functions or the other types of functions we've been seeing. So this light is, I don't know what's going on with this light. It's kind of sketchy. No, it's worse. All right. Anyways, okay, so all right, there we go. So let's look at this first table. So we want to see that the x values are changing by a constant amount. It's changing by 2 each time for this first table. And that's fine as long as the x values are changing by the same. And the y values, though, are also changing by the same value of 2. It's always increasing by 2. So what we have is a constant rate of change, or a constant ratio of change. And yeah, this is going back to our old friend, the linear function. This is not an exponential function, this is a linear function. Because a linear function has a constant rate of change. In this case, it would just be 2 over 2, which is the same as 1 over 1 or just 1. And you're like, well, how does it make sense? Well, think about it. Well, you always should be thinking that in math. If we were to put if we were to have include x equals 1 in here, then what would the y value be below it? It would be halfway between 2 and 4, which would be 3. And so then the y values would be changing by 1 if x is changing by 1. So they're changing at a 1-to-1 ratio or the same. And the equation here, remember, y equals mx plus b, our typical slope-intercept form, which we call essentially a linear function because it has a constant rate of growth m, which is 1. So we have 1x plus, in this case, b is like the y-intercept, or the value that the graph intersects the y-axis, or when x equals 0, which is 2. So this first equation is y equals 1x plus 2. So it's the same thing, it's just a different language, and we're not graphing it. That's why we don't really say slope or y-intercept, that sort of thing. We say initial value, we say, rate of change, because, that's going to work in all contexts. So this is the time in your math lives where you really have to start paying attention to those concepts, because that's the only way you're going to survive, really. Let's keep on going. Next, we got x changing by 1 each time again, so that's all good. But the y values, wow, they're multiplying by 3, then by 3 again, then by 3 again. And so we have a constant factor, which is 3. That's what we mean by exponential. It's being multiplied by the same number over and over. This constant factor is the base. So the base b is equal to 3. And again, the initial value or the starting value or the value when x equals 0 is 1. So initial value is equal to, we denoted with the letter A. So it's putting it all together slow at first. Yeah, remember the exponential y equals A times b to the x power. I don't know what's going on with this pen. It's giving me some difficulty. But if we fill it in, we will get y equals 1 times 3 to the x power. In this case, the 1 is not really necessary to write, but let's just do it for fun because it also sticks out and lets us know that the a value is 1. So we have our first exponential equation. All right. Let me write exponential function here. I normally write smaller and neater, but for whatever reason, I'm not right now. All right, the next one we got x is changing by 1 again, going up by 1 each time. Plus 1, plus 1, plus 1. But the y's are doing something where we have it's first being multiplied by 2, then multiplied by 3, then multiplied by 4. And so this is going to be neither exponential nor linear. Neither exponential nor linear. Don't fall into the trap of calling it exponential because you see multiplying. That's why we say constant factor, because the factor has to be the same. You have to be multiplying by the same number each time. And we're not going to worry about the equation here because this is something that's not really easy to derive, or there's no set formula. Maybe sometime in the future when you go into mathematics as your major, we'll see it again. But anyways, for now, let's move on to the D. We look at the x values. They're going up by 1 again, so we're good. The y values multiplied by 2, multiplied by 2, multiplied by 2. And so we got a constant factor. So we have an exponential function. In which we have the y equals a times b to the x power. Remember, the a is the initial value or the value when x equals 0. And so it's going to be 4. So we have 4 times, and our base or our constant factor is 2. So we have 4 times 2 to the x. Now leave it like this. Do not put y equals 8 to the x. This is very wrong. It is so wrong. I'll be very disappointed if I see that in my students doing it, because it basically just makes everything fall apart and not make sense in exponential graphing and equations. So just don't do that, please. I don't even want to see it. Okay, now let's look at evaluating exponentials. We'll get back to studying patterns later on, but we want to first be sure that we always know how to do the order of operations and how to evaluate exponents, because if you don't, you're basically going to be screwed and you're going to have, a very tough time in this chapter and really not be able to survive. So we want to first be able to survive in this unit. So we need to know how to evaluate exponentials. So let's do some practice, yeah? Let me get a sip of water first. Okay, so maybe it'd be a good idea, or if you want to see how you're doing, you can try some of the problems ahead by pausing the video and then unpausing it to see how you're doing. But I'm going to be going through every single one in detail with all the work, because that will be very, very clear, and we will know exactly what I am doing. So let's go through these first couple ones slow. So we're going to evaluate this for x equals 2. So we're going to have y equals -3 times 4 to the 2 power. This is the same as -3 times 4 to the 2 power is basically saying that we're going to have 4 times 4, which is basically, or not basically, it is -3 times 16. And our answer is -48. Let me switch to pencil. Experimenting with the light. Okay, that's too dark. All right. Next, we got y equals 2 times 0.25 to the x power. So we're going to evaluate this for x equals -3. Now, this is basically going to go against all your beliefs, but you're actually going to want to change this into a fraction, which I know many students are traumatized and will always try to get away from fractions as much as they can. But in exponents, you really have to learn to get along with them, because they're going to help you be precise and accurate, which is necessary for, achieving greatness in this exponential chapter. So we're going to write 0.25 as 1/4 instead. And that's because we need to learn how to take care of this -3 exponent. We don't want it to be negative. We want it to be positive. And so what we're going to do is we're going to flip this 1/4 to make it 4/1, because by doing that, that's going to make the exponent into a +3. Yay. Then this is much easier to evaluate. So we have 2 times 4/1 times 4/1 times 4/1. I'm going to leave it as a fraction, just so, again, you can really understand how these fractions work conceptually and be very, certain that you're doing all these right. And so this is just 2 times 4, 4, 4, 4, 16, 64 over 1. 2 times 64, because 2 is the same as 2/1. Multiplying across, we have 128 over 1, which is just 128. See, so it all works out nicely. Okay. So like now would probably be a good idea to try C and D, the next two on your own. See how, how well you're understanding this, but I'm going to go through it regardless. Okay, so next we got, use a pen. We're going to evaluate this for 3, and I'm going to go a little faster now since we've gone through some examples. -2 times 5 to the 3rd power equal to -2 times 5 times 5 times 5, which is -2, 5, 25, 125, and bang, -250. Simple. All right, some negative action. Y equals 3. We're going to make this 0.5 into 1/2. 3 times 1/2 to -2. Let's change that -2 into +2 by making this equal to 3 times 2/1, all to the +2 power. This then becomes 3 times 2/1 times 2/1, which is then equal to 3 times 4/1, which is just 12/1, or just 12. All right. And this light is bothering me. Yeah, whatever. Okay, next one. Now we're gonna step up our game. I'm gonna move this light, it's annoying me down here. See if that's better. Not really, but whatever. Let's get into some of the more fun ones now, where we really have to be clear on what we're doing. So here we got y equals -8 times 0.75. Let's make up 0.75 into 3/4 to the x plus 2 power plus 7 after. And we're going to plug in 2 for x. We have to the 2 plus 2 power plus 7, which is equal to -8 times 3/4 to the 4th power. Go step by step when you first learn this. Like, you will be surprised at how much it helps and how well it makes sure and it helps ensure that you do everything accurately. Plus, it's fun to see all the steps. You're going to look smart and feel smart to feel like your work done. Now, we're going to have -8 times 3/4 to the 4th power. And even though this is a fraction, all we're doing is the same thing as we would do with any number. We would have 3/4 times 3/4 times 3/4. Did I say the 3/4 times 3/4 times 3/4 times 3/4? So 4 times. Plus 7 at the end. Just like we would with any other number. And from here, we get -8 times 3 times multiplying across 3 times 3 times 3 times 3, 9, 27, 81 over 4, 16, 64, 256 plus 7. All right. Now with this, let's recognize that -8 over 1 is the same as -8. And so then we can just multiply -8 times 81, which is what, 36 -6. 8 times 80 is 640, so this is -648. I hope I did that right. -648. -648 over 256. Again, we just multiply across plus 7. And actually, so the 7, I'm gonna cross this line here. Break some. Should I? Yeah, I'm gonna do it. So the 7 over 1, we need to combine it with this -648. Actually, I'm not. I'm gonna do it over here. I feel bad crossing that because the other problem is gonna feel squished and he's gonna be mad at me. So -648 over 256 plus 7 over 1, and to make it so that it has the same denominator as this, because the same denominator as this one, because that's what we need to add them. We're going to multiply this by 256 over 256. And so we then get -648 over 256 plus 7, just multiply across. The bottom will be 256. 7 times 256. 7 times 256 will undoubtedly give you 1792. And from here, we just add the numerator. So we know it's going to be all over 256. 1792 minus 648. Why is the calculator so dark? 1144. All over 256. Now we can simplify this into breaking it down, and we eventually get 143 over 32. But don't worry about that because this is really the key to this. You want to make sure you get an accurate fraction. And here and only here at the end is when I allow you, if you're in my class or around me, to then rewrite this as a decimal. And the reason is because if you try to round fractions earlier in the problem and by changing them into like approximate decimals, you're going to have more of an inaccurate answer, because you're basically doing all these operations after an incorrect answer because technically it's rounded. And the more you do, the more inaccurate it becomes. Here we don't do anything after, so this will be the most precise if it's a decimal. I'll explain more as we go through this, but just trust me. Plus, this is, again, this looks cooler. Okay, next one. We're going to evaluate this. I'm going to use a pencil here. For x equals 2. A little faster now. Y is equal to -2. Change the 0.25 to 1/4. x plus 1, so 2 plus 1, or let's just make that 3 right away, plus 6. And we get negative 2 times 1/4 to the third power. So we just have 1/4 times 1/4 times 1/4 plus 6. We get negative 2. 1 times 1 times 1 is 1. 4 times 4, 16 times 4 is 64. Plus 6. And here, remember, this is just a fraction. Negative 2 over 1 times 1 over 64 gives you, what's going on here? Gives you, I'm going to switch to pen. Negative 2 over 64 plus 6. And now we got to just change the 6 so that's over 64. So remember, 6 over 1 is the same as 6. And we're going to multiply by 64 over 64. And in case you need a refresher as to why we do that, it's because 64 over 64 is just 1. And we're just multiplying by 1. And because we multiply by 1, we're not changing the value because we don't want to do that. That would be wrong, and we'd be doing the math the wrong way. We're just changing the way it looks. It's like if you go to the store, I'm going to give you 100 cents or $1, or I'm going to give you like 4 quarters. It's all the same. It's just different ways of representing the same thing. That's why we're always putting equals as we go through the problem. Now from that, we then have negative 2 over 64 plus 6 times 64 on top, so 360, 384 over 1 times 64. And then we just add negative 2 and 384, so we get 382 over 64, which reduces to 191 over 32. Again, this is our final answer. If you want to then convert it to a decimal here, that's fine. But just don't do it before. And we get the decimal 5.96875. And this one is actually, the one before I actually don't need to put approximately because there's no, this is exact. It's not being rounded. Okay, final 2 of these guys, because we want to be certain that we have this stuff mastered, of course. All right. So try to, again, see if you can do these first on your own. But here I go. Watch and learn. Or just watch or learn. Y equals negative 2. That's 0.35. In case you're ever like having difficulty changing a decimal into a fraction, whatever that number is can always be over 100. And from there you can reduce, divide by 5, divide by 5. And so then it'll be just 7 over 20. So this is the same as negative 2 times 7 over 20 to the x minus 4 power, so or 1 minus 4 power in this case, minus 9, which is equal to negative 2 times 7 over 20 to the negative 3 power, minus 9. Jump into the next line. Switching pens. We get negative 2. We're going to flip this guy because we want to make the 3 positive. So we get negative 2 times 20 over 7 to the positive 3 minus 9, which then becomes equal to negative 2 times 20 over 7 times 20 over 7 times 20 over 7 minus 9 afterwards. Okay, making progress. We get negative 2. 20 times 2400 times 8,000, yeah. 7 times 7, 49, times 7 again, 343. Minus 9. Man, I can feel the excitement. Negative 2 times 8,000 is negative 16,000 over 343 minus 9. This 9 is the same as 9 over 1. And so to combine it, we're going to multiply by 343 over 343, which is equal to negative 16,000 over 343 minus the 9 times 343 only on top. 9 times 343. Again, I don't know why it's so dark there. 3,087. Over 343. And from there, we just subtract that. We get negative 19,087 over 343. And that's really our final answer. We can approximate this decimally speaking. 19,087 divided by 343. We get, oh, cool. What a number. Actually, let me move this over here. Maybe maybe I'll have more light here. A little better. Let's write that number there. Actually, hard to see still, but I apologize. So this is going to be an approximately 55.64723032. Write all the numbers. Please don't be one of those that is like, oh my God, I don't want to write all that. It's so much work. And, they don't. And then, they just, then are, cursed for the rest of your life because they don't want to write a couple of numbers. It's really not that hard. Well, it is. It's fun. You should. There's no excuse. Even if your pen runs out of ink, you get a new one. Here you go. I'm going to move this again up here. Maybe that works. Oh, yeah, it does work better. All right, one more of these guys. Okay, so we have 0.55 in there. Again, you can write that as 55 over 100, which is the same divided by 5 as 11 over 20. And so evaluating, we get y equals negative 3 times 11 over 20 to the 2 minus 5 power minus 4 zoom in, pushing pencil, negative 3 times 11 over 20 to the negative 3 power minus 4, exploding. Let's make that negative 3 positive 3. So we have negative 3 times 20 over 11 to the positive 3. Then we subtract 4 from there, which is then equal to negative 3. I'm not going to set it here, so let's just move on to the next line. Negative 3 times 20 over 11 times 20 over 11 times 20 over 11 minus 4. And again, yeah, I'm showing every step. So don't be like, why is it showing so much work? Is there a fast way to do it? I mean, it's not necessarily a faster way. You're just doing some of the calculations in your head. If you know, like, that's 20 to the third over 11 to the third, which is fine. I actually like when my students do mental calculations because I think it's good for you. But I know that I'm a teacher, so it's always good for me to show every step because there will always be some students who maybe need different, visuals than others, or, who knows? And I like it sometimes. So we have negative 3 times 20 times, so 2,400, 8,000 again. 11 to the third should be like 1331, I believe. It's like, I remember because it's like a reflection, 1313. Which I don't know why I actually remember. And then we multiply across. -3 times 8,000. And -24,000 over 1331 minus 4. And what I'm going to do is use the power of the sticky notes to finish the problem here. So carrying on. Whoops, there we go. So carrying on to here, -24,000 over 1331 minus 4, remember 4 over 1, times 1331 over 1331. 4 times 1331, 5324. Minus 5324 over 1331. Which gives us -29,324 over 1331. Nice. It's awesome. And a decimal approximation will have to be 29,324 divided by 1,133. Obviously be 22.0315552. Cool. Nice. See how much better you feel about yourself when you're able to do these cool calculations? Here's my duck, for some inspiration. And feel free to take a break. So I'm going to pause the video and then probably run to the restroom, and I'm going to continue on to graph. All right, so I am back. So are you. If you left or never left, it's all good. But now I'm about to embark onto an exciting part of the journey, which will involve graphing exponentials. And this is where it really gets cool, or I mean cooler, obviously, because you will see exactly how powerful these exponentials can be, how fast they can grow, and how how great and like curved, and just say it really will blow you away when you think about the size and magnitude these things get to from just small numbers, and you will know what I mean in just a few minutes. So let's get going. So we have this definition that talks about the graph of an exponential. So let me read it. The graph of y equals a times b to the x is a vertical stretch or vertical compression by a factor of the absolute value of a. It's the graph of y equals b to the x. Now, don't worry too much if you're a little like, what the hell does that mean? I mean, what the heck does that mean? Because it's like a more formal way to think about transformations or like graph or changing equations. But just think of like whenever you change a number into another number, if you were to do it geometrically, like if you were to change, let me use this yellow pad. If you were to change the number 3, let's say something is 3 units tall, 1, 2, 3, right? If you were to change this into the number 6, it becomes 6, then it's, represents something that's 6 units tall, That's not 1, 2, 3, 4, 5. Ignore this. This is actually the surface of the building. So 1, 2, 3, 4, 5, 6. And so what are you doing? Like geometrically speaking, you're stretching this by a factor of 2 in that way. You can think of this by adding 3, but when you're talking about, let's say you have y equals, in this case, a b to the x versus b to the x. So you have y equals 3 to the x versus y equals 2 times 3 to the x. You're basically changing this equation by multiplying or stretching it vertically by a factor of 2. And so we're going to look into that. But it's always good to understand these ideas when you're doing math, because when you understand the concept, math is beautiful. And you'll realize just how great it is. But if you don't, then you may be traumatized and scared of it. But here I go. So we have this graph of y equals a times b to the x power. The y-intercept is going to be equal to the value of a, meaning that I'm going to put this in parentheses. I'm never sure if I should put it in parentheses, but I am. So we have a graph. This is our x-y axis. And these things give you an idea. These graphs are going to start looking like this. The y-intercept is, the point here. That's going to be at 0, a. So whatever the a value is in the equation, that's going to be the value on that graph, or where it intersects the y-axis. And so we have a couple different cases that these graphs can fall into. And so one thing we also need to know is let's also write and when, so we can be grammatically correct. And when the a value is negative or less than 0, in other words, you think of the graph as a reflection. What is up with this pencil? And when a is less than 0, the graph is a reflection in the y-axis or across the y-axis, or across the x-axis, I mean. The graph is a reflection in the x-axis. I'm going to say in because that makes you sound really mathematical, sophisticated. But you can say across. It's typically how the common folk think of it, which is not really wrong. But if you say in, you're more mathematically precise. But anyways, let's go through some examples of how these graphs can appear. Case 1. In case 1, we have that the base b is more than 1 and that a is in positive. So what will happen is, making a sketch, x-y axis. And I forgot to mention, before that, the graph, so these exponential graphs can basically fall into one of 4 cases. So the first case is, b is more than 1, a is positive. It's going to look like this shape. It's going to be increasing. And it's going to have, again, an intercept at 0, a. The domain will be all the real numbers. So x going from negative infinity to positive infinity. And the range will be from 0 upward. So will be 0, infinity. I like using interval notation, but you could also write, you could write it like y is greater than 0. I like interval notation, I just do. So I usually will write it by that, in that way. Okay, so how about we do well, actually let's go through let's explain the second case. Second case, we have that the base is still more than 1, but a is negative. So what happens here? Well, talking about this is basically what was saying here. We have a reflection in the x-axis, meaning that instead of it going like this, you reflect it across this line, flip it over, and the graph does this sort of thing. Wow. And this point is still 0, a. And you're like, wait a minute, how's it 0, a? It's below the x-axis. Well, yeah, because it's negative, and that's what this says. So that's why it makes sense. The domain is still the same, all real numbers from negative infinity to positive infinity, but the range kind of goes the other way because we're going from negative infinity up to 0. So we're going to have negative infinity in parentheses, comma 0 in brackets. Or again, you could say, or y is less than 0. They're both correct. Let's actually go through an example first before we go to case 3 and 4, so you can really get a good sense of what's going on here. So we're gonna graph this equation for these x values, and these are given to you at first just because I want to make sure you guys get a clear sense, or basically to give you like a head start and focus on the shape of the graph rather than what numbers do I pick. I'll talk about that later on. So we're just going to evaluate for these 5 numbers, and I'm going to use my pen here. So we're going to use function notation. So we have f of -2, f of -1, f of 0, f of 1, f of 2. So this is basically why I spent the previous part of this lesson doing those evaluation problems, because you want to make sure that your problems, or you don't make any mistakes here. This should be like the easier part. Like it would be terrible if you make a mistake and can't do these calculations and the graph looks like a mess. So make sure you master the evaluation of exponentials first. Anyways, so we just plug -2 into there. So we have 5 times 2 to the -2. And again, I'm going to go a little faster than the first, but this is the same as 5 times 2/1 to the -2. But to make it positive, we're going to flip that fraction and make it 5 times 1/2 to the +2. Which then is going to give us 5 times 1/2 times 1/2, or 5 times 1/4, which is 5/4. Or, I know I'm going into the graph, but I'll be all right. 1.25 for the first point there. All right, next let's evaluate for -1. 5 times 2 to the -1. Making the exponent positive, we have 5 times 1/2 to the 1. This is simply just 5 times 1/2, or 5/2. Or just 2.5. Next, we got 5 times 2 to the 0. Okay. Who out there knows what this is? Because this is one of, students will, be like, oh man, what is it? This will get you, because it's also one, it's because it doesn't really make sense unless, you actually study it. And I will explain exactly why this is later on, or in another video, because it's kind of cool. But again, it's not intuitive. So it's not going to be 0. It's actually going to be 1. 2 to the 0 power is 1. Any real number to the 0 power is always 1. And so your answer is just 5. 5 times 1, or just 5. F of 1, we have 5 times 2 to the 1. This is just 2. So 5 times 2, which is then 10. And last and least, 5 times 2 to the 2. 5 times 4, and we get 20. And so you can see there's no axes on these graphs. I did that intentionally because I'm smart, or because I wanted your graph to be made from the values you get, obviously. Because you can see these numbers start to get very big, going from decimals all the way to up to 20. And so let's make it so that we can fit as many as possible. So we're going to put the y-axis a little more over here. 1, 2, 3, -1, -2, -3. And let's go by 2s so we can fit all these values. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And let's plot them. -2, 1.25. And don't worry, it's like sometimes my students freak out, like, where's 1.25? Is that where it is? Yeah, it is. Just use common sense, be approximate. I'm not going to bring a microscope or a measuring device when I'm grading these tests. So -1, next one, -1, 2.5. So about over here. 0, 5 here, 1, 10 here, and 2, 20. So you can see how this thing is growing, very, very fast. And I'm not going to say the pattern yet, but those of you some of you are probably catching on to the power, or what you're going to be like, isn't there a trick? Yeah, you can think of it as a trick. Think of graphing these as a trick, but I'm not going to tell you the trick, because if I tell you the trick, you're not really going to understand it, and you're just going to try to look to do things quickly. So if you can figure it out, great, but I'll tell you what it is at some other time. Now let's write out what the domain is. This will be negative infinity to positive infinity, and the range will be 0 to infinity. Now, yeah, you technically actually don't even have to put the x and y, because you get to a point in your math lives where it's supposed to be common sense. But, here I put them anyways, just to remind you all. And remember the concept behind what domain and range are. They're basically all the values that can come in and out of the function. So this equation, we can plug in anything. So the domain are all real numbers, because we can put any value in for x. But from these values are only going to come out positive values. There's no way to get a negative number from any value. So you can either think logically about that, or just the graph will show that. Now, that being said, we have this special line here that I almost forgot to mention, but it's so cool I have to mention it. I'm going to use a green pen because it's Christmas in like a month or two, and because this is the only other color I had. But we have this boundary line known as an asymptote. Asymptote. A very cool name, which is basically a line that the graph will never cross. And it has an equation. In this case, it is y equals 0. Like, what's the purpose of an asymptote? You might ask. Well, there are, very important reasons for him or her, or whatever it is. The main thing is for it to basically serve as a guiding line to how to graph the function. For like when you get into more advanced equations, you're gonna have asymptotes that are like slanted, and have graphs that have various shapes like going up, down, and so they're really gonna make a lot more sense in their usefulness. But right now, you really just want to understand what they are, which again is a line that this graph will never get to. It will get super, super close to it, infinitely close, but it will never actually be 0. Okay, so let's look at some other graphs now. Let's see if I've done. So that was an example of case 1, as you can see. The next one will be this guy over here, which we haven't done yet. Well, we haven't done the case, so let's go back to this page and let's talk about case 3. Case 3 will be when b is between 0 and 1, so a fraction, and a is positive. So think about what would happen. I want to see if you can figure out what the graph shape will be. If b is between 0 and 1, and a is positive, that means the graph will always be positive, because a positive to a positive will always be positive. But what will happen is the values will actually get very, very small. Will get infinitely small. They'll continuously get small. So it's going to do this. It's going to get infinitely close to the x-axis. It will still cross at 0a, but it's going to do this. It's going to basically decay or decrease, with the domain still being negative infinity to positive infinity, and the range being positive numbers, 0 to infinity. And finally, case 4, we will have where b is between 0 and 1 again, but a is negative. Just like the case 1 and 2 were related, these two are going to be related as well by being reflected across the x-axis, and so this will look like that. They'll be upward towards the x-axis from the bottom, still crossing at 0a. It's just a reflection across the x-axis Domain is negative infinity to positive infinity, but the range will be all negative numbers, so from negative infinity to 0. Cool. So let's look at an example of this. Problem B. And now I'm going to start going through the calculations quickly because that's not what the important part is. But try them first on your own and then check back by unpausing the video to make sure you get it correctly. So I'm going to go through a couple of these graphs. The first one being, or the next one being this one. So we're still going to evaluate for -2, -1, 0, 1, and 2. And let's make that 0.25 1/4. Yeah. So this is -1 times 1/4 to the x power. Plug in -2, we'll have -1 times 1/4 to -2. Making that -2 positive, we're going to flip the 1/4. This will be -4/1 second power. This will be -4 squared is 16, or just 4/1 times 4/1. This will just be 16, or just -16. Nice. Next one, we'll have -1 times 1/4 to -1. Here, all we got to do is flip that fraction, so we get -4/1, which is -4. I was slanting to the side. F of 0, we get -1 times 1/4 to 0. 1/4 to 0, who remembers? It's 1. So negative times 1, or -1 times 1. If you were noticing, I was saying -1, because I want you guys to remember there's technically like a -1 here. So it helps students to remember to do that multiplying after you raise the exponents. That way you avoid a deadly mistake. And so then we get -1, not 1 here. Keeping the fun going, we get -1 times 1/4 to the 1, which is just -1/4, or -0.25. And f of 2 will be -1 times 1/4 to the 2, which is just -1 times 1/4 times 1/4, or 1/16. So we get -1/16. As a decimal, that will be -0.0625. So this is an example of case 2, or sorry, not this case 4. Because see, the b is between 0 and 1, a is less than 0. b is 1/4, and a is -1. I actually just said that at the beginning. My apologies. b is 1/4 and a is -1. So this is case 4. So that will give you an idea. That will help, to make sure you're graphing this correctly. So it's going to be below the x-axis. So let's draw our x-axis higher up. Y-axis over here. 1, 2, 3, -1, -2, -3. And we just need to get to -16. So again, we'll just go by 2s, -2, -4, -6, 8, -10, -12, 14, -16. Just do the math and graph. -2, -16, -1, -4, -1, or 0, -1, 0.25, and 0.1625. We got this guy. Wow. And we will say, or the domain and range will just be what we had this earlier. -infinity to positive infinity. The range will be y is below 0, or -infinity to 0. asymptote will be the x-axis again. Nice, because it gets very, very infinitely close to the x-axis, but never crosses the line at y equals 0. Okay, and keeping the fun going strong, we have, for our next problem, f of x equals -4 times 2 to the x power. So a is -4, b is 2. What case do we have here? Let's see, a is negative, but b is, greater than 1, so it's not going to be this one. A is negative, but b is greater than 1, so we got case 2. So we know our graph will look something like this. Just for some reference. So let's plug and chug this guy. So f of -2, f of -1, f of 0, f of 1, f of 2. Powering through now. We get -4 times 2 to the -2, which is -4 times 1/2 to the 2, -4 times 1/4. Get -4 over 4, just -1. Again, that's why we spent that time going over those practice problems where you evaluate those cool calculations. F of -1, we get -4 times 2 to the -1, which is -4 times 1/2 to the 1, or just -4 over 2, which is then just -2. F of 0, -4 times 2 to the 0, or -4 times 1, which will then just be -4. F of 1 equal to -4 times 2 to the 1, or just -4 times 2, -8. And f of 2 will be -4 times 2 to the 2, or -4 times 4, which will be -16. And again, it'll be below the x-axis since it's case 2. And the numbers are showing this. So we're going to have a graph like this. 1, 2, 3, -1, -2, -3. You got to get to -16. So let's go by 2s. Let me switch. Graph the points. -2, -1. Over here. -1, -2. Here. 0, -4. 1, -8. And 2, -16. And we got this guy. All right. And domain and range, I'm just going to write D to save ink. Next is going to be all real numbers once again, and the range will be all negative numbers. Negative infinity to 0. And same asymptote, the line y equals 0. Don't worry, we'll get to some more complicated and fun equations for asymptotes. So, just hang tight. Let's just go through one more for now. Here we got f of x is 3 times 1/2 to the x power. All right. All right, so in this fourth case, we have f of x equals 3 times 1/2 of the x power. So a is 3, b is 1/2. And so then we have an example of case 3, right? Let's see, case. Yeah, so it's going to look something like this. Just for reference. Okay, so let's get to it. Let's do the math. So f of -2, f of -1, f of 0, f of 1, f of 2. I'm going to switch pens. I don't like the way that one looks. Here we go. 3 times 1/2 to the -2. 3 times 2/1 to the 2. 3 times 4, which gives us 12. F of -1 is 3 times 1/2 to the -1. 3 times 2/1 to the 1, making that -1 positive 1. So it's just 3 times 2, and we'll get 6. F of 0, 3 times 1/2 to the 0. 1/2 to the 0 is 1. 3 times 1 is 3. Cool. F of 1 is 3 times 1/2 to the 1, or 3 just times 1/2, or 3/2, or just 1.5. And f of 2 is just 3 times 1/2 to the 2, 3 times 1 to the 2 over 2 to the 2, 3 times 1/4, 3/4, or 0.75. Okay. Making our graph. X-axis, check. Oh, whoops. Y-axis, double check. Numbers. -1, -2, -3. 1, 2, 3. Let's go by 2 so we can get all the way up to 12 at least. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And let's make this graph. -2, 12. Bang. -1, 6. Bang. 0, 3. Double bang. 1, 1.5. 1.5 bangs. And 2, 0.75. Like over here. Maybe that 1.5 should be a little more. Here we go. Here's our graph. Yeah. Makes sense. Asymptotes. It is again the line. Asymptote. The line y equals 0. And the domain is all real numbers again. And the range is all positive numbers, 0 to infinity. Okay, so there's 4 examples of exponential graphs showing the 4 general cases. And again, you can see why we need to make sure we master our calculations. This is why I make sure my students spend their time doing these types of problems and being precise and accurate, because when you get to graphing, you don't want to be worried about this. You want to be just doing the graph. This should be the easy part. This should be the elementary part at this point. So make sure you got this mastered by doing plenty of these types of practice problems. Okay, so you feel free to take a break and do what you got to do. But I will now move on to 2 of the final graphs, and special graphs that you usually will not see in a, you know, in a Math 1 course or a freshman year math course or just a beginning algebra course, because they have, you know, very unique asymptotes and behavior. But I like to show them to my students so they can really start to see what's going on. But just so you know, you're usually not tested or expected to know this in an elementary algebra course, and they're really no different. But the conceptual questions about them will be. But without further ado, here we go. So we have this next equation being y is equal to 3 times 2 to the x minus 1 power minus 3. So we want to see like what those you know, interesting equations look when you're doing stuff to the exponent. So again, let's just make sure we know our calculations, and we're going to evaluate for -2, -1, 0, 1, and 2. And again, we don't technically have f of x, but let's just make this f of x so it's easier to write out. So f of -1, f of -2, f of 0, f of 1, and f of 2. All right, so I'm going to power through these faster again because, you know, that's not the important part, but let me go through this first one slowly. I just contradicted myself, I know. F of -2 is 3 times 2 to -2 minus 1. -2 minus, well, let me just put it all together. -2 minus 1 minus 3. So 3 times 2 to the -3 minus 3, which is then 3 times 2 to the -3, which is basically 3 times 1/2 to the 3 by flipping this fraction, minus 3. And I'm going to put this up here so it doesn't get in the way. So 3 times 1/2 to the 3. So 3 times 1, so 1 to the 3 is 1 over 8. 3 times 1/8 minus 3. 3/8 minus 3. And since this is a perfect decimal, this will be about -2 point, or let's just do it. Negative minus 3 is 24 over 8. So -21 over 8. I'm running out of space here. I usually don't do this, but -21 over 8 is our answer, which is about -2.65. 21 divided by 8. Yeah, -2.65. I'm running out of space. Well, make sure not to do this on the next calculation because I don't like messy work. I got too excited to complete it. All right, f of -1. Three times 2, -1 minus 1, next to -2 minus 3 equals 3 times 2 to the -2, which is just going to be 1/2 to the 2, minus 3, which is basically 3 times 1/4, minus 3, which will be 3/4 minus 3, which will be -2.25. F of 0 will be 3 times 2 to the 0 minus 1, or 3 times 2 to the -1. Then we minus 3, and this will be 3 times 1/2 to the 1, minus 3, which will then be 3 times 1/2, or 3/2, minus 3, which would then be -1.5. Cool. F of 1, 3 times 2, 1 minus 1 will be 0. 3 times 2 to the 0, minus 1. 2 to the 0 is 1, so we have 3 times 1 minus 1, or 3 minus 1, or just 2. Pushing back to pen. 3 times 2 to the 2 minus 1, or 3 times 2 to the 1 minus 3. 3 times 2, which is then just 6 minus 3, will then just be 3. So let's go from here. So let's recognize that we have the A value is 3, the B value is 2. And so what case do we have? Case we got. I can see we have case 1. They're both positive. Case 1. So let's cross this, yeah? Do-do-do. One, two, three, -1, -2, -3. And we only need to go by ones because we can fit all the numbers. 1, 2, 3, 4, 5, 6. And as we start plotting these, we will get, for the first one, -2, -2.625. So we get something like this, somewhere around here. Then we get -1, comma -2.25, something like this. Then we get 0, comma -1.5. And we get 1, comma 2. Or wait, no, 1, comma. Did I mess up here? 3 times 3 times 1. Oh, wow. That should be a 3. 3. Interesting. Bet some of you were in the comments yelling, and I heard you. Well, no, actually, well, I felt something strange here. Where I got you. So then this should be 0. And it will make sense. We have 1, 0, and 2, 3. And what you're going to see is we have a very interesting equation here. If you were to go further, we would get this at 3, 9, 7, 8, 9. Let me put that up there. Now here's the thing. If you keep on plugging numbers in, because let's not go, let's just do this for now. You have an asymptote down here, but let's make sure that you understand what the number is. So I'm not going to run through the calculation. I'll just put the number so you get the idea. So if I was to calculate for -3, -4, f of -3. If I did f of -3, I would get -2.8125. You know? So then I would have another point like around over here. So I can keep on going, but let's go big. Let's say if I did -100. Let's say f of -100. You know, and now we're talking, we would get 3 times 2 to the negative, so -100 minus 1, -101, minus 3 equals 3 times 1/2 to the 101 minus 3. And let's use this calculator power to, demonstrate what's going on. We have 1/2 raised to the 101 power. And see, you get this very, very small number. This means that there's 31 0, or this is going to be moved to the 31 spots to the right. So let me actually write it so you can see. Well, let me multiply this by 3, then subtract 3. So this times 3, then subtract 3. I get -3. It gets so close that the calculator can't even deal with it. But what's going on is, let's do this. This would be basically 3 times, let me see if I can get this right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 25, 26, 27, 28, 29, 30, 31. Wait, that's where my 3 is going to be. So 3 will be here. 3, 9, 4, 4, 3, 0, 4, 5, 3. Then I'll subtract 3 after this. That's what this calculator is saying here. See how cool this number looks? Now, what is this getting at? Is that, see, this number is probably, you know, so small and so that doesn't even matter. You're just gonna treat it like 0. If someone told you if I told you I'm gonna raise your grade by this much, you're not gonna be like, oh, cool, thanks. You're gonna be like, who cares? This is basically 0. So 3 times 0 is what this is gonna basically be equal to. 3 times 0 minus 3. So that 3 times 0 is 0. 0 minus 3 is negative 3. And that's what the calculator does. You get so tired of doing that, it's like it's negative 3. It doesn't matter. It's so close that we don't need to worry about all those number digits. And this is what happens with the asymptote. We have an asymptote. It's such an interesting word, asymptote. Kind of funny, but our asymptote is this line, the line of y equals 3. That is our asymptote. We'll never get beyond this line. So that's what you'll be seeing and dealing with in your future math courses. But I like showing you guys earlier so you can, you know, really get a sense of what they're used for. And what happens is also changes the domain and range. So, the domain actually stays the same. I mean, it's still not, so it won't change the domain. That's the domain. But the range will be changed because what will happen is that the range or the y values will start from this line. It'll be from negative 3 upward. So we're going to go from negative 3 comma infinity. And this should say negative 3. I realized they wrote positive 3. Let me fix that. I'm going to write this in black actually because it'll stand out better. So our asymptote is y equals negative 3. So that's the deal here. So let me go through one more of these guys. But again, these are bonus problems. These are if you want to push yourself to that next level and, you know, demonstrate how great you are at the math. So let's cross this. Same values. So let's make this f of x. So we're going to have f of negative 2. 4 times 2, negative 2 minus 3 to negative 5 plus 2. 4 times 1/2 to the 5 plus 2. This ends up being 1/2 to the 5th power. Whoops, 4 times 1, 2, 4, 2, 4, 8, 16, 32, 1 over 32 plus 2, 4 over 32, or just 1 over 8 plus 2, which will then be 2.125. It's a decimal. And again, I'm going through these faster now because that's not the focus here, or shouldn't be anymore. F of negative 1, 4 times 2 to the negative 1 minus 3, so 2 to the negative 4 plus 2, 4 times 1/2 to the 4th plus 2. So 4 times 1/16 or 4/16 plus 2. So 1/4 plus 2 will then be 2.25. F of 0, 4 times 2 to the 0 minus 3. So 4 times 2 to the negative 3 plus 2. 4 times 1/2 cubed plus 2. 4 times 1/8 or 4/8 plus 2. So this is just 1/2. 1/2 plus 2, and you get 2.5. Oops, 2.5. F of 1, we'll get 4 times 2 to the negative 2 plus 2. 4 times 1/2 squared plus 2 is equal to 4 times 1/4, or this just becomes 1. So 1 plus 2 equals 3. And then last, f of 2 is 4 times 2 to the negative 1 plus 2 is 4 times 1/2 plus 2, which is just 2 plus 2, which is 4. Nice. And identifying our a and b values. A is 4, b is 2. And again, we have a case 1 situation. So keeping our x's or keeping our y values above the x-axis. 1, 2, 3, -1, -2, -3. And we can just go by ones for this one. 1, 2. Plotting these points, -2, 2.125. -1, 2.25. 0, 2.5. 1, 3. 2, 4. Growing really, really slow, eh? Now I'm gonna give a giveaway. At 3, you're gonna get about number 6. And for 4, you're gonna get the number 10. But now let's see if you can guess by looking at this, what would the asymptote be? What do you notice the numbers are approaching down here? Can't actually hear you, but I feel that you guys are saying, well, it's gonna be 2, the line y equals 2. You're correct. This is the asymptote. Line y equals 2. The values will get very, very close to 2, but we'll never reach it. And again, we can show this by, let's say it's make x like -1000. So 4 times 2 to, like, let's say the -1003. We -8024. Wait, hold on. Plus 2. What am I doing here? 4 times. Oh, I did not do that correctly. Raised to the -1003. Obviously, we get 0. And then let me add that 2, of course. Let me get 2. See, that's what happens. Let's see what happens if I do 4 times 2 to -50. Will this still be 0? 4 times 2 to -100. No, whoops, no. 4 times 2 to the -100. Still having decimals. I'm just having fun here. But this is your graph again. And then so the domain here will be all real numbers again. And the range will then start from -2. So we're going to have from -2 or parentheses around -2 to positive infinity. All right, let me get some water. Awesome. The math really burns those calories, and you need to make sure you stay hydrated to perform at your best. All right, the final 2 problems in this first lesson deal with bacteria, which I know you guys are very excited for. Let's see what it says. The graph represents a bacterial population Y after X days. Oh, wow. It's cool. Right, an exponential function represents a population. Find the population after 6 days. Not a problem. We know the equation for exponential is y is equal to a times b to the x. We got to find the a and the b. What is the a? Well, a is the initial value. So what does it start with? Let's zoom in here. So you can see at 0, we have 3. So a is 3, because that's what it started with. And we go from 3 to 9 to 27 to 81. And so you probably get the picture, or probably know the calculation. Our b is 3 as well. And so our equation is y is equal to 3 times 3 to the x. Do not put y equals 9 to the x. Do not do that. You hear that, students of mine? Do not do this. It is not equal to 9 to the x power. If you do that, I don't know. I'll probably cry or something. Or I'll probably like cover my crying by trying to act tough. But please don't do that. It comes such a long way. Anyways, so one more of these. Write the exponential function that represents the population for this bacteria. So again, we'll use that same exponential. So let's find what the a and b values are. Zooming in. Almost the same. We have 0, 3, so the a is 3. And then we go from 3 to 12 to 48 to 192. And so the base will be 4 because you're multiplying by 4 each time. Oops. The b is 4. And so we combine them to make our equation. Y is equal to 3 times 4 to the x power. All right. Oh, I forgot to do part B. Find the population every 6 days for this. So for that, we just do y of 6. We plug in 6. So 3 times 3 to the 6th power. 3 to the 6th power, 3 to the 6th power is 729. And so we get 2187. For this one, find it after 5 days. So we're going to have y of 5 is equal to 3 times 4 to the 5th power. 3 times, what's 4 to the 5th power? Well, that's 1024, obviously. And 3 times 1024 is 3072. Yes, 3072. And bang, you got it. You're done with this first lesson. So here's my duck to represent the accomplishment. Yeah, that was very involved lesson, especially if you have been, well, if you're in like a math 1 or elementary or algebra course where you're first learning, where you were first learning about, linear equations, graphing, and solving systems of equations. When you jump to the exponential unit, students tend to get really be like, oh man, I'm actually gonna have to study and learn stuff now. So just just accept that that's what you got to do in this class from now on. And so don't be scared. Just stick with it, because exponentials are different and they are going to probably be something that's new you haven't encountered yet. But you just gotta put in the correct work ethic, and you're going to figure out how they work, and it won't be too bad. But yes, I would bet you that from my experience, a lot of students do get somewhat scared, I'll say, when they first have to deal with exponential equations. And so that being said, please give me any feedback or any comments or advice on if you thought I did a good, bad job, or whatever. Maybe I went over something fast, slow, or just I don't know. I like to think I can take criticism, but I'm a teacher, and so I want to do my best. And so please let me know. But if you liked it, thought I did good, yeah, that'd be great as well. And so hit that like and subscribe, of course. Yeah. I'll see you in the next video. Okay, bye.